Hello everyone, this is our group ASCG, and this is our phase 1 of the civil design project. You're probably wondering how we came up with this extremely creative name. We just spent weeks and weeks on trying to jumble our first letters of our names together, and we came up with ASCG. And our mission statement is ASCG realizes dreams to make it your reality. So I'll give it off to George to start us out.
All right, so first, my name is George.
My name's Antonio.
Christian. Sid.
And today we're going to discuss with you our plan for the phase 1 of this project. So this is going to be located in central Manhattan. It's going to be a 40-story building, and it's going to be a combined 16,500 square foot, and 13,800 is going to be used in office space. So as you can see here, this is just a 2D model of what our floor frame is going to look like. As you can see, we have many different types of beams here in terms of like the entire floor plan. And this is the 3-dimensional version of what our floor plan is going to look like. And here's another visual on what our 3D will look like.
Here you finally see the analysis of the actual structure that structural design that we came up with as a team. Here you see the moment diagram for the live loads that are going to be present inside the office building, which is about 100 square feet per square foot, 100 pounds per square foot, sorry. And as we know that computer models are a very useful tool, but they're not very reliable 100%. We always have to confirm if the calculations that it gives us are accurate and are going to actually serve the purpose that we need to. So here we have the hand calculations of the beams that are going to be present, and here we have the tributary area of the beam that's going to be holding up, along with the analysis of the shear diagram as well as the moment diagram. And here we have the same process of calculations for each of the columns. These are just 2 examples of the beams and columns that are going to be present inside the building. We did this process for each one of the beams to ensure that the computer model is accurate. And here are just more diagrams of the dead load in this case of the building.
And this chart represents the shear diagram as well. Since it goes hand in hand with the calculations, we look into computer analysis for both the live load and the dead load that it pertains to. And this represents the displacement of the floor for the building as structure with the placed columns and flooring and a beam design. And here we came up with the material list of what we got used so far, which we will continually update as the project goes on, as it will pertain to our final project to calculate total costs. And then throughout the development process, we're going to consider various factors, such as the design dead loads, along with design live loads and concentrated loads, which cover various little standards that we have to keep in mind in terms of the weight that each factor can keep as we go through the project itself.
These are some of our established parameters for our structure. So as you can see, we start with our ground snow load because we are located in Manhattan, so we can't we have to consider the different weathers that we have to come into play with. This is also some of our parameters for the foundation design, which is our unit weight, and we have the angle of internal friction, which comes out to 30 degrees. I'm literally reading these out to you, but we're also seeing that we have a solar compression, which gives us a footing width of 4 feet, which is also in 4,000 pounds per square feet. And we also have the footing width coming out to less than or equal to 4 feet, which comes out to 6,000 pounds per square foot. And like I said, we also are in New York, so we're faced with a lot of wind, and that's something we also came out to calculate as to 115 miles per hour. And this gave us an exposure with a category of B. And going along with the wind, we have a wind importance factor of 1, and the max wind deflection we calculated was 0.62 inches.
And that concludes our presentation.
Good morning. I'm James Lavender.
I'm Joseph.
I'm David.
I'm John.
I'm Matt.
And we are High Rise Structural Design Co.
Yeah, so our mission statement is design tomorrow today. So at High Rise Structural Design, we kind of want to implement and have unique designs without sacrificing safety. or practicality. We live on the cutting edge of structural innovation. Yeah, so this is our project description. It's a 40-story commercial high-rise building. It's composed of steel beams, steel girders, steel columns, concrete slab with metal deck, and it has a concrete core. So this is the formwork that we work with.
So I'm talking about the design criteria. So all our criteria is derived from the New York City Building Code Manual, the 2014 edition, Chapter 16. So our typical floor height we had to use was 15 feet, and this is what we used for our entire project. We also had the design with a concrete strength of 4,000 psi, and the rebar that we must use had to be 60,000 psi, and this was the ASTM standard 615 grade 60 bar. All our steel beams had to be 50,000 psi, and this is equivalent to the ASTM standard A993 grade 50 bar. And lastly, the required soil bearing capacity was 10 tons per square foot, so this is important when we figured out all the loads going down into our footings. And then next we have the design loads. So again, all our loads were derived from the ASHO HB 13 New York City Building Code, the 2014 edition, Chapter 16. For the dead loads, we had to design with 20 pounds per square foot for all the structural beams, columns, and slabs, and another 20 pounds per square foot for all the non-structural things, like all the elements in the building, such as like the furniture, the mechanical systems, and the electrical systems. We also have live load, so that's 70 pounds per square foot for all the people in the room, and you'll see how each of those three different items add up later in our calculations. And then lastly, as we go up in the floors, we needed to design for 20 pounds per square foot for the wind load and another 20 for the snow load.
Okay, so just some normal the dimensions and specifications for each of our floors. So for the 40-story building, here's just one of the models in ETABS and then a render model. So for each floor, it's going to be roughly 150 by 110 feet, totaling in 16,500 square footage. And then the spans between the supports and beam spacings, so just 30-foot spans, 40-foot spacings. And then for all vertical beams, 30 to 40 foot, and then 10 foot. And then for each of the individual bays, be roughly 30 by 40 feet. And then for the slabs and decks, 3-inch metal deck, and then 4.5-inch concrete slab.
So here's our typical floor. Note the columns along the perimeter and the concrete in the center, concrete core. Here's our beam design. We have W18 by 40 for the longer span girders. We have W16 by 26 for the shorter span girders, 24 by 62 for these interior long beams, 18 by 35 for the short interior beams, also 18 by 35 for the perimeter beams running along the width, and finally 21 by 50 for the perimeter beams running along the length of the building.
Alright, so here we have a sample calculation for a live load. We decided to do the sample calculation with this girder right here. It's in between one of the 30 by 40 sections that we had in our floor plan. So first off, we found the tributary width to be 10 feet, and we used a live load of 70 pounds per square foot. So then we had to make it a two-dimensional calculation, so we multiplied 70 PSF by 10 feet to get 700 pounds per foot. Once we got, I converted it to 0.7 kips per foot to make the calculations a little bit smaller. So then the first step was to find the maximum moment value. So we took the load, which is 0.7 kips per foot, times the length of beam, which is 40 foot squared, divided by 8. This is the standard formula to find the maximum moment, and we got 140 kips per foot, which is exactly what we got from ETABS. Then we did the max shear, and since this beam is symmetrical, we could just split it in half and find the force going up there to get the max shear. And I found that to be 14 kips, which again matches the ETABS calculation. And here's all the representations of each of the forces and moments on the beam. So then now we have the material takeoff. This is for all 40 floors. As you can see, we have the majority of the beams are the W18 by 40, which is over 1,000. We have W21 by 50 beams for a length of 12,000 feet. The 18 by 40s are 44,000 feet. These other beams aren't used as much, but it's still a lot. We also have the weight of all of the metal decks and concrete decks and the weight of the walls.
Thank you for listening. Any questions?
Hey, good morning, everyone. We are Towers Incorporated, and my name is Nadine Tilly.
I'm Caitlin Barbaro.
My name is Joel.
I'm Shivani Patel.
And today we'd like to present to you our 40-story commercial building. So our project is basically a 40-story commercial building with a 1-story basement, and it's going to be centered in the center of New York City with an overall height of 600 feet, with each floor being about 15 feet tall. And the overall gross area would be 16,500 square feet from the 150 by 110 floor frame. So when designing this building, we had to take into account the New York City building codes, the 2014 edition, and this was to make sure we are in compliance with all of the newest standards. And when we were planning the floor plan, we had to ensure that beams were 10 foot on center, and that we had 2 main girders, one on the north end, one on the south end, and that they were at least 30 feet apart. And for our core, we decided to go with the concrete core, and this allowed the most efficient design for elevators. It provided extra fire protection, and it also added some structural stability to the center of the building. We have to also take into account some design live loads and design dead loads. So this is just a list of a few we had to take into account for a commercial building that included lobbies, offices, whether it be the flooring or the actual furniture, the stairs, the exits, the elevator shafts, and the equipment rooms, along with some dead loads such as the concrete, the facade, the landscaping, and the flooring. For the composite floor framing, we decided to go with lightweight concrete. For the metal deck of the frame, we had a 3-inch spacing with the overall concrete depth to be 3 inches and 3.25 inches. And this allowed for additional fire protection, and it's overall the best for lightweight concrete.
Here we have a typical layout of our floor plan with composite beam and girders that we designed for. The interior beams are mainly designed with a typical I-beam section width of W18 by 40. There are a few exceptions being W16 by 26 and W21 by 44. That is because it was the most feasible option for our ceiling heights and other requirements. Then we have our girders, which are typically W24 by 55 as well as W21 by 44. Next, please.
All right, so for our beam selection, we thought for using W18 by 40. We realized that it satisfied our design loads. The moments and shears were satisfied. ETAPS actually does a pretty nice job by giving us different types of beam selections, and we noticed that it was the most economical and the lightest one. So in conclusion, we would opt out using W18 by 40. And for uniforming, can you please go back one slide, please? ETAPS recommend us to use another beam section, but to keep the uniformity in this side as well as this side, we kept it 18 by 40.
So like Shivani mentioned, we also did use W16 by 26, and we used that in our center in between the elevators. So we decided to opt for the change in this section because it would allow for the smaller beam, we would have a higher floor height. So architecturally, we wanted higher ceilings. And then further than that, it was the lightest section, so most cost efficient. And then on top of that, since it was in the center, it was surrounded by our core framing. So it did have a smaller span to go across, and it did have the structural support of the core. So we decided to opt for the lightest section for this part.
And this is a report that was provided by ETAPS, where it essentially calculates based on the design loads, the shear was satisfied, as well as the construction bending moment and partial bendings. They're all satisfied. And this is for W1840. As well as right here, it shows that the allowable, everything were satisfied based on the selection. We also ran our beam selection through Excel that was provided by the professor, and we inputted all the parameters that were provided for the top slab, the deck, everything was calculated through Excel, and we concluded that, next slide, that it was all okay and satisfied. Therefore, we opted with the 18 to 40 for the most of our, that was mostly composed of our floor framing.
Here we have the same analysis for the girder. For example, we have an example from W24 by 55. As you can see, ETABS gives out a couple variable beam sections that are applicable for the situation, but we went with the lightest one because A, it was economically more beneficial, plus it also allowed us for the ceiling height that we wanted. As you can see, we ran with a composition action of 90% here, giving us a total deflection of 0.1243, and where the allowable is 0.125, so it meets our requirements. And here again, we had the report telling us that everything works out and the design is adequate. He also ran the Excel calculations with composition action of 90% again with the beam section that we chose, and as you can see, the design was approved and the calculations ran through. As you can see, we found that this beam design works with our floor plan with studs, 94 studs required and no camber necessary.
So now, even though we're using a computer programming, we still need to hand check all of our results. So here we just have an example for our design for shear. You can see in the end, ETABS generated 20 kips, and when we did our hand calculations, we assumed it was a pin-pin connection, and we also got 20 kips. So that aligned correctly with what our ETABS gave us. We also did the same thing to design for moment, and once again, we got the same answers for ETABS. It was for our axial loading that we got slightly different answers. In our hand calculations, we got 60 kips where ETABS generated 64. So we looked into why this may have happened, and in our actual ETABS model, you can see that the floor framing overhangs past the columns slightly. So this is automatically included into the ETABS calculations, but it's not given a definite length of overhanging, so we didn't consider that in ours. But since it is just off by a little bit, it still passes the check. Next, we have just our basic material takeoff where we consider it for columns, beams, and concrete. We went by weight here since in the end, most of our costs will be generated by the weight of material that we are using. So this is just general and starting. And in the end, we do plan on kind of calculating our total costs and then manipulating it to see if we chose different beams, what would be the most cost efficient. But for right now, we do just have this general layout and number of steps. Any questions?
All right.
We are HDIB. My name is Jose Rodriguez.
My name is Alexis.
My name is Diego Cabrera.
And my name's Lara.
So, Diego will get started.
So company name HDIB, inspired by HNTB, Hispanic owned firm. If you can guess, HDIB stands for Hispanic Student.
So moving on, our mission statement. What is our mission statement, you might be asking? At HDIB, our mission is to provide innovative and efficient design solutions that meet the unique needs of our clients. We strive to ensure that every project we undertake is completed with the highest level of quality and accuracy, while also taking into consideration the environmental impact of our work. Our goal is to build strong, lasting relationships with our clients by delivering exceptional service, clear communication, and a commitment to exceeding their expectations. We believe in continuous improvement and ongoing learning to stay at the forefront of our industry and deliver the best possible outcomes for our clients. And here are our beautiful signatures. Not really, but yes.
Okay. So the project, so what are we designing? Our project entails a 40-story commercial building located in the center of Manhattan, New York. So the building footprint is 110 feet wide by 150 feet, taking up a square footage of 16,100 square feet. So Our typical floor height right now is 14 feet, subject to like changes as the project progresses. We might bump it up to 15 or 16 depending on how things go. And our typical bay area right now is 30 by 40 feet with columns spaced at 30 feet up by on center. So the scope of our project, in order to like make this building possible, we have to design several components to make the whole building come together. So our project scope composes of a composite floor framing system, beams, girders, columns to transfer the gravity loads into the foundations, which will then the foundation will transfer those loads into the subsurface conditions of the soils. We also have to consider a foundation system to support not only the building loads, but also like distribute the load safely so we don't see excessive settlements and bearing capacity failures. And we also have to design a lateral system to resist seismic like lateral loads in our design because we are in a high wind, not so much earthquake, but we also have to consider wind since our structure is going to be really tall. We have to also consider wind and seismic loads. And at the end of our project, once we're all done, we're going to provide estimated material quantity takeoff in terms of how much material we're using and how much does it cost overall.
So these are design criteria, the same design codes that we all have to follow for our 40-story buildings. All structural works shall conform to the International Building Code. We're going to follow ASCE 710, minimum design loads for buildings and other structures, ACI 31811, and AISC 360. Yeah, all standard design codes that we all have to follow. And we're going to be following it, using it through our design.
So here we have our typical composite floor framing plan. This is our first floor. So we have our concrete core, we have W16 to W24 beams, steel columns. And we are using the live load as 70 pounds per square foot and a dead load of 20 pounds per square foot. As we continue to design the structure, these values here, the kinds of beams that we have are subject to change. We have typical floor framing is 3.25 inches, lightweight concrete on 3-inch metal deck over composite steel beams and girders, ordinary reinforced concrete shear wall, and steel columns. And that's all.
That concludes our presentation.
Hi everyone, so we are JDLA Engineering, Building the Future. I'm William Stover.
I'm Anthony. I'm Giancarlos Valerio Reyes. I'm Giovanni Patel.
So the purpose of our project is the safe and efficient design of an office building. We're going to use the ETABS 19 software for the structural design, and our goal is to comply with the New York City Building Code. So our site is 621 West 45th Street, which is currently a parking lot. This will be the footprint of our building, and it's between 45th and 46th Street on the west side of Manhattan. Our floor plate is 150 feet by 110 feet, and there's 16,500 square feet per floor, which is 660,000 square feet for the entire 40-story building. So our design criteria are to follow the 2022 New York City Building Code, and within that, our design loads are determined by ASCE 7. Concrete will follow the ACI 318 standard, and steel will follow the AISC 360 standard. So our design loads, we have the dead load, which is based on the actual weight of materials that we used, the superimposed dead load, which is 20 feet, and the live load, which will be between 7 and 100 pounds per square foot.
So this is going to be the design of our floor framing. So for ours, we decided to go in with a low bearing wall for the elevator shaft. So this right here is going to be a low bearing wall. And this is how the floor framing is going to look. This is going to be a 3D view of our first floor, and this is the 3D view of our entire building. So here with it, using ETABS, we're able to do the live load of finding the moment using the live load and the dead load. So we, ETAP is a computer, so it's a tool. So even though that we were able to put in our inputs with the 70 live load, and it was able to give it the moment, we also had to do hand calculations to be able to just confirm that this is the moment that is going to be assigned to the beams. So we did, ETAP gives you a report, and like the other team said before, it gives you all the checks. It makes sure that all the calculations are correct, and or for example, we use when we were using ETAPs, we used the ACM 310. That was the code that we used. So ETAPs checks to make sure that all the codes are followed during their inspection. So like again, it's giving you all the numbers that you need. The loading, the strength check, the construction survival check, and next one, I'll go back. So in give you the beams. So my part is going to take care of the other part.
So it's always beneficial to double check your calculations, since not every time machines give you accurate numbers. So we did have calculations to verify our ETABS results. So we did we checked we put a apply load, live load 100 at the surface square, and by considering tributary weight, we did the moment, we find the moment, and we got 150 kPa per foot, which is exact with our ETAB result. That's for 30, 40 beam section, 30-40 floor section, and that's for 30-30 flex section. And we got the exact number with the ETAB. Similarly, we did calculations for column as well by counting the tributary area of 20-30 section and 30-40 section, and we got the same result with ETAB. We also did load calculations for metal deck, and as we know, we have 4.5 inch of concrete, 3 for metal, and half inch we added as you take off the metal pieces throughout the section. So that's how we counted everything, and the total applied load we got was 627, and then we went over the moment, which we got slightly off than our ETAB result.
Okay, so this is our beam layout. Our beams rate between W24 beams and W14 beams. The W24 beams are right here. They take up most of the loads, which is why they're the biggest. And the ones on the edges, like the W14 and W16, they don't take up as much load, so they can be smaller. As you can see, the majority of the structure is composed of W18 and W18 by 35 beams, which is the purple ones on the sides. And the total count of all the beams, we're going to see it in the next slide. So this is the material takeoff. As you can see, as mentioned before, the W18 by 35 take up the most amount of linear feet, and the ones on the edges take up less, like 24,000 or 2,400 and 4,800. And the floor slabs take up 660,000 square feet.
Yeah, the thing is also for us, the ETAP model gives you the design, something that will support your design. Well, now we have to get into sustainability and what will be most cost effective for the beam size that we're going to use and floor framing. So the ETAP gives you an example of what you could use, but now as part of the design phase that we're going to go into next, then we're going to determine which was the most cost effective and sustainable beams that we could use.
Alright, so good morning everyone. We're the Rex Structural Group, and my name's Rikesh.
My name's Steve.
My name's Evan.
My name's Carlos.
And our mission statement is REC Structural Group strives to serve the community needs by providing our expertise in design and construction. We pride ourselves in efficiency, attention to detail, and teamwork. And our values focus on client success, sustainability, and integrity. And today we're just going to go over basics of our design, and Steve's going to present that. And Evan's going to go into the details of design loads, and Carlos is going to show the shear moment deflection for our floor framing design.
So before you go into the design criteria, determining the loads and some of the other criteria that we need for a design, we have to, one of the most important tools is ATC hazards, and that's used for design. Now, the way that you use this tool is that depending on the location of your project, which ours is in Manhattan, New York, you're able to get values from ASC, such as the snow load, the wind, seismic, that you later on use through the codes, ASC and the IBC. But you're supposed to use the New York IBC because there's different, the codes don't all work for, how would you say it? There's specific codes for specific states. Like in California, you have seismic loads that are way greater than the East Coast. And in our case, Manhattan, you have to use a specific code. And again, before you go into the design criteria, like the loads and everything, you have to determine some of the geometrical, some of the measurements, which includes the height of the building, the floor height, some of the concrete strength that we're using, soil bearing capacity, and reinforcement. And again, some of the applicable codes include the IBC, the ASC, and specifically the one that we have to focus on is the New York City Building Code.
So for our construction dead load, we have 20 pounds per square feet. For our live load, we have 100 pounds per square feet. And for our superimposed dead load, we have 35 pounds per square feet. And for our load combination that we used for our analysis for our shear and moment, we did 1.2 dead load plus 1.6 live load plus 1.2 superimposed dead load. So for our floor framing design, our dimensions are 150 by 110 feet, and this is composed of W24, W18, and W16 beams, with W18s being the primary beams, all spaced out at 30 feet on center, with the W24 beams spaced 10 feet in between each one, so 2 between each W18 beam. And for our structural slab, it's a composite slab with a 3-inch metal deck and 3.25-inch lightweight concrete.
So here we have the shear output given from ETABS, and in order to validate this, we did hand calculations. So you can see we have 30 by 40 foot bays with 2 intermediate beams in the bays. So that gives like a tributary width of 10 feet for each intermediate beam. In order to calculate the shear, we did the tributary width times the pounds per square foot to get a linear foot in order to use the shear equations for a composite beam. And then we also did the same thing for moment, but using the moment equations for composite beams, and we did come out with the same values that were given in ETABS. And then we also checked the deflection. So for the allowable deflection for live load for a composite beam is L over 360. So with our length of 40 feet, we did 40 over 360 and got a deflection of 0.11 feet. And the deflection given was 0.12, so it was just in the allowable deflection.